Okay, so hi everyone. So what we're going to do today is a short tutorial on modeling synapses and networks using NEURON. Since the whole focus of the course is on NetPyNE and network building with NetPyNE, we're just going to see this as a brief, short example to illustrate the basics. But we'll build like more complex networks and more detailed network models on the next coming days. So today is just gonna be really like a 3-cell network and showing some recurrent connections and some of the basics of how to implement this in NEURON, which of course is quite helpful to understand also when you start modeling using NetPyNE. So I'm gonna give a brief overview of the basic process of how NEURON implements networks. And as you saw with Bill, there are some specifics, some nomenclature that is a bit different from the biology to the actual NEURON implementation. So we just want to clarify this before we start so it's clear what we're talking about during the tutorial. Oh, and just to mention, so we're going to try a new setup where we are all in the same group. We are 30, 35 or so. So I think it should be okay. And if we have any issues, then we'll split up in a separate room or via Slack. The other tutors, Joe and Joao, can answer some of the questions. Okay, so we'll start with this very simple scenario where we have a presynaptic cell and a postsynaptic cell. So the first concept we need to know is what we call synapse in NEURON is really the postsynaptic receptor of the cell. So of course, in reality, in biology, when you talk about a synapse, you have both the presynaptic side and the postsynaptic side with different components in each. But in terms of implementation in NEURON, when you talk about synapses, this is really just the component that is part of the postsynaptic cell. So almost like the synaptic receptor. This has a set of parameters that we will discuss later, including the equilibrium potential, which of course tells you what type of synapse it's going to be, excitatory or inhibitory, and the time constant, which gives some delay for the inner dynamics of the synapse. Okay, so the other big component that Bill already mentioned as well is the netcon, which is really establishes a network connection or network connector between a source of voltage and the postsynaptic synapse, postsynaptic cell synapse. So the netcon is really, as Bill mentioned, a detector of voltage. And so when this voltage crosses a threshold, usually -10, although you can change it, then it sends an event to the postsynaptic cell. And it tells, hey, on this side, on this cell here, in the presynaptic cell, the voltage crossed this threshold, and so we think this is a spike. So do whatever you have to do on your side to make sure this spike has the effect it should have. Okay. So again, two major objects that implement synaptic connectivity in NEURON. On the postsynaptic cell, you have the NEURON synapse, and then you have the NEURON netcon, which connects the presynaptic cell to the postsynaptic cell. It measures the voltage in the presynaptic cell and sends an event to the postsynaptic synapse, postsynaptic cell synapse. Parameters of the netcon. So we have the weight or the strength of the connection, which can be something like the amount of neurotransmitter, but could also be equated to other things like the amount of synaptic vesicles. There's a number of things of biological parameters that are sort of combined into this parameter called the weight. And then we have the delay, which is the time from the delay or the time between the spike happening in the presynaptic side and when it reaches the postsynaptic side. So this again simulates a number of things, including the release of the synaptic vesicle, transmission of the spike along the axon, and so on. Okay, on the postsynaptic side, we have the equilibrium potential, which I just mentioned, and this tau time constant, which models the inner dynamics of the synapse. So what happens in the synapse side is that usually it depends on how the mod file that implements the synapse is written, but the most simple one basically change the conductance of this synapse. A synapse, as we know, is really just a special type of channel that has its conductance modulated by whether you have received this kind of events or not. And so when the spike is received by the postsynaptic cell, it just increases the conductance of this channel, and so ions flow in, and you get these postsynaptic potentials, which can be excitatory or inhibitory. Okay, so let's see again, just step by step, the different things that happen in a synaptic connection in neuron. So the first thing that would happen is that you get a presynaptic spike. So the presynaptic cell generates a spike for whatever reason. They might have inputs from other cells or a current injection. And so the NetCon in the presynaptic cell detects that the voltage has crossed the threshold. Here it says 10 millivolts, but it's usually -10 or 0. And so it will send an event to the synapse on the postsynaptic cell. It will send this event to make sure it reaches the postsynaptic side after the delay that was established in the NetCon. And this event will include some information, which is the weight or the strength of the connection. On the postsynaptic side, once this event is received, it will modify the conductance or do whatever other complicated thing the mod file we're using is implementing. And it will modify this based on the strength of the connection, on this weight that we mentioned. So the synapse, then the currents that flow into this channel in the synapse will generate a new postsynaptic potential, which will be an EPSP or an IPSP, depending on the equilibrium potential of the synapse. Okay, so these are the basic steps, and now we're going to go ahead and implement this in code. This is another just summary slide with the basic things that I just mentioned. And here is just to say that we have many different types of synapse. The one that we're going to be using is the simplest one, the exponential synapse, XSyn. And there's one that is kind of an artificial synapse, the alpha synapse, which you can basically activate at any point in time. So you don't need a presynaptic cell to activate it. So you can just simulate inputs, synaptic inputs. And of course, there are many other complex models of synapses, for example, that include dependence on calcium and so on. Here's the syntax for how we're going to create these different objects. So for the NetCon, we are going to create it in this way. We give it the variable a name, for example, con equals h.netcon. Then we have to provide the source of the voltage. So where are we going to be recording this voltage of the presynaptic cell? The target, which will be typically a synapse, a synaptic object. And we have to include the section of this source, so where it's going to be, where the actual voltage is going to be recorded. And this is not very clear why it's required. It's one of those things in NEURON. I don't know if maybe in the latest version it's not included or not, but basically we just have to follow the convention and include the source section, so where the voltage is coming from. For example, we might have a netcon, h.netcon, with the source of the voltage coming from the center of the Soma 0.5. And we have to use, as we've seen before, for example, for recording the voltage, where we use this underscore ref underscore. The target will be a synapse that is called syn. And in sec, we have to include the Soma, which is where we are measuring the voltage. We can then set a number of parameters.
What do you think is unnecessary here?
I know it was before in previous Neuron versions. I was hoping it was removed at some point, but I haven't really tested it.
It's not removed. It's still required.
Okay.
There's a plan for it if anybody wants to make improvements to NEURON/NetPyNE as their project. Happy to talk with you about it. But it has to do with threads, and if you're running a threaded simulation, telling it what section is involved helps it figure out which thread owns that netcon object. It's mildly frustrating that even when you're not using a threaded simulation that you still have to have it, but you do.
Oh, well, it's not that bad. Okay, so the other main object that we mentioned, well, these are the parameters of the netcon, the delay and the weight. Oh, okay, so we're done. So we have synapses and we have netcons. So now we can move on to the tutorial. And for this, I'm going to switch to the Google Colabs. So these instructions here in the slides are actually copied over to the Colab. So if I switch here, do you see the Google Colab now? And do you see it full screen?
Yes. Yeah, we can see your browser. Yeah.
Perfect. Okay. So this is the setup that we're going to have. This is the first part of the 3-part tutorial, and this is like the simplest example. So we're going to have 2 cells. Oh, yeah, so to follow this example, just as you've done before, copy this Google Colab, make a copy of the Google Colab so that you can edit it and run it yourself. The links are in the general channel of the Slack workspace. So yeah, so in this example, we just have 2 cells, the presynaptic cell and the postsynaptic cell. And we are just essentially going to create one connection, a single connection from the presynaptic cell. Remember, you need to create this netcon and a synapse on the postsynaptic cell. That's essentially it. And then, of course, you need to provide some stimulation to the presynaptic cell to make it do something. So we're just going to have an input here, a current injection that's going to generate a spike in the presynaptic cell, and that is going to generate, in turn, a postsynaptic potential in the postsynaptic cell. So below are the instructions. Here is just the installing the Neuron simulator as usual. And the first piece of code was something that we've sort of followed from previous exercises in another course. And it's just a basic class of a cell in Neuron. So we're not going to go into the details of this, but the idea is that I think Robert also showed a similar example, that you can create cells, objects of cells, just referencing a template class. In this case, the class is going to be called H8cell, and it does the basic things. So it creates 2 sections, a Soma and a Dendrite, connects the Soma to the Dendrite, adds some geometry here. It's a simple cell with a round Soma and a 180 micron Dendrite, similar to what you see here. And then it adds some basic biophysics, the Hodgkin-Huxley channel with the sodium and potassium, passive channel in the Dendrite, and then has a number of methods that you can call to do optional things. So for example, you might want to add a current stimulation to the cell, and you can do that by calling the method addCurrentStim. That basically creates a current clamp with some fixed parameters. You can also record the voltage, which of course is something useful we've been doing as well. And it by default records the voltage in both the Soma and the Dendrite. And then you have a method to plot the voltage. Okay, so these 3 methods are optional. You can call them if you need them. And the other ones are called here at the top in the constructor. So for all cells, they will happen. So below here are the instructions for you to fill in. So the first three instructions are together, and the idea is that you go here in this code and write whatever you need to do them. So the first step is create a cell called pre-cell1 of the class HH cell. Okay, that should be a line. Then here we have, it says adapt the addCurrentStim method to accept delay as an input argument, and add the current stimulation to pre-cell1 at 20 milliseconds. So this one is actually asking you to make a modification in this cell class, which is just a nice exercise to make sure that you understand what this class is about. And you basically have to modify this method here at addCurrentStim to allow for a new argument that sets the delay. The delay? Yes. Okay, so you're all experts in Python, so this should be relatively easy, but we'll go, of course, over it in detail. And finally, record the voltage of the cell. So that would be calling this method here. So the way I've done this in the past is I give a period of time for the students to do each of the steps, and then we go over it. Usually I will ask some student to provide their solution, and then we go on to the next step. So we're gonna try that. So for the first one, maybe we can have 5 minutes. I think it's relatively simple, and we'll see how it goes. If you have any questions, please post them to Slack, or if you want here to the chat on Google, but better to Slack. And you can also ask here in the Google Meet in person.
So where is the link to the collab?
It's in the general channel.
Sorry.
I can post it again. Sorry, you're cutting off. I'm going to post it again. It's in the general channel. Did you get it?
I get it.
Anyone else, please, if you're having trouble finding the collabs or setting this up, please let us know. Okay, so I think we're gonna go ahead. So maybe I'll try just calling out people in the order I have them here so that everybody has a chance to participate. So the first one on my screen is Marco Peña. Did you have a chance to finish?
No, to be honest, not.
Okay, so let's give a couple more minutes then, because you also have to set up the Google Colab panel. No pressure, Mark. Okay, so I can guide you through this, don't worry. So maybe we'll try the first part. So create a cell, pre-cell 1 of the class H8 cell. Have any idea how you might do this?
You only have to call the class.
Just pre-cell 1 equal to the class.
Pre-cell 1 equal to H8 cell.
It's also
Like this. Anything else?
brackets.
Okay. Very good. Step 2. So adapt the add current stim method to accept delay as an input argument and add the current stimulation to pre-cell 1 at 20 milliseconds. Marco, you want to give it a go?
I think I get it. Just modify the definition of add current where self-esteem dot delay as a variable.
Okay.
And then
What
add
would be the
self comma delay. Self comma delay. I think that's all. Well.
Perfect. That is perfect. And then how would you call that function here?
Writing that function. I'm not sure at that point, but I think it's just the function at current brackets pre-cell comma the delay 20 comma 20. I'm not sure if we have to add units. I think it's
no, you don't need to add units in this case. So this is almost correct. This is almost correct, but since this is an object, the syntax is you put the name of the object first, pre-cell 1.
Okay. Yeah.
And then call the method of that object, which is add current stim. So you were almost there. Okay, very good. And the last step, record the voltage of the cell.
Just pre-cell one dot record underscore voltage, and then just brackets.
Perfect. Okay, so we call the method called record voltage from this pre-cell one. Okay, very good. So let's move to the next step. It says add a post cell of class H8 cell and set up recording of voltage.
I have a question.
Yes?
To record the voltage cell, why we didn't use the H point vector?
So we are actually using, but it's built into the method of this class. So if you see here the definition of record voltage, it does everything that you were doing before inside this method. And the results, the vectors that contain the time and the voltage are stored within the cell object. So for example, self.tvec will store the time, will record the time, and will store the time here inside the object. And self.vvec Soma will store the voltage of the Soma, and self.vvec then will store the voltage of the Dendrite. So this is useful because each cell will store its own voltage. And so you don't need to have like 1,000 variables outside of the cell for each of the voltage recordings.
Okay, thank you.
No worries, thanks. Okay, so this step here should be pretty easy as it's very similar to the previous one. So let's give a couple minutes. Okay, so the next one on my screen is David Donofrio. Are you with us?
Yes.
Okay.
Sorry, I haven't finished it.
Okay, no worries. Sorry, I was a bit quick.
Okay, so you would just label post cell 1 is equal to the HH cell class.
Okay, great.
And then post cell dot record underscore voltage.
Okay, fantastic. Thank you, David. Okay, so the next step is really the most relevant to this tutorial, which is related to the connectivity. So here it says, add an excitatory synaptic receptor called post-syn at the dendrite of post cell. And it should have a reversal potential of 0 millivolts and a delay of 2 milliseconds. So what I'm gonna do is share the slides that I was using, which contain all the information you need to do this. Let me see. Yes. Okay, so I'm gonna git link and I'll paste it in the general channel. So if you download that PDF, you will have all the information you need to know the syntax of how to create these Synapse objects.
Just a question. Instead of delay, wouldn't that be decay time constant?
This is the time constant. Yes, you're right. Sorry.
Okay.
Oh, okay. Okay, so if anyone had trouble downloading the slides or has any questions, please let us know.
Salvador, can I ask a question?
Yes, of course.
Why we use a half 0.5 as an argument in this post sign one when we are creating the postsynaptic cell or
Why do we
receptor?
use what as an argument, sorry?
The 0.5 one.
Because synapses are point processes, which means they have to go at a specific segment. Unlike distributed mechanisms like channels, which can be placed on a whole section, and those are distributed along all the segments. This is a point process, so the synapse has to be placed at a specific location of the section, and that is indicated by this 0.5. This is the location we call, which corresponds to a particular segment. So if the dendrite had 100 segments, it would go in the middle one, then 50 or 51, and yeah, usually it has more. Sometimes it has only one segment, so it doesn't really matter, but you still have to do it.
Okay, perfect. Thank you.
Okay, so the next one I have on screen seems like he has finished, so I'm going to ask him. Philippe Schlegel.
Right, hold on. Pull up my code. So you would do that by 5. What are postsim1, if you want to call it that.
Okay.
Your call really equals h dot x sin, and then you would do in brackets post cell 1 dot dend, another set of brackets 0.5, and then new line post in 1 dot e equals 0 times millivolt.
We're gonna omit the billing calls because I think we didn't use them here, but yeah, that's correct also. By default, it's millivolts, so it's the same. And next. So there's one line missing. Sorry.
Oh, oh right. I think that the what was it? The delay is by default 2 milliseconds, right? So I didn't change that. Sorry, it's post in one dot delay.
It was actually, sorry, that was a mistake in the slides. It's actually, it should be time constant. So the decay time constant of the synapse.
Oh, yeah. Well, in this case, post in one dot tau equals 2 milliseconds.
Okay, perfect. Tau equal 2. Okay, great. So yeah, so notice we are creating this object, exponential synapse. We are placing it in the postsynaptic cell at the dendrite section at location 0.5. Please call the post cell just post cell, not post cell 1, because we only have one postsynaptic cell. And so for the rest of the exercise, it might be confusing if you have a different label. So we have pre-cell 1, pre-cell 2, and post-cell. So everyone keeping up? Any questions about this part? Okay, so let's move on to the next step, which is add a connection between the pre-cell 1 Soma and the post-cell dendrite, where we just added a synapse. And the connection should have weight 0.002 and a delay of 1 millisecond. So remember, we have added, we have added this synapse here in the postsynaptic cell, and now we want to add the red arrow, the connection going from the voltage of the presynaptic cell to the synapse of the postsynaptic cell.
Is there a threshold?
We didn't change it, so whatever is the default.
Okay.
So I'm gonna run. What? Okay, so this one is a bit more tricky, but let's give it a go. Suri, are you there?
Yes.
Okay. Wanna give it a shot?
Okay. So I did pre-1 con.
Okay. Great.
Is equal to h.netcon.
Perfect.
And the source would be the pre-cell Soma. So pre-cell 1.Soma 0.5
Great.
dot underscore ref underscore v. So it's being recorded from there, that voltage, and it gets
Fantastic.
inputted. It gets input into the post cell dendrite, which is post syn 1. So comma dot underscore ref underscore v comma post syn 1 comma no post syn
Great.
1. That's it.
Yes. Okay.
And then pre-1 con dot weight is equal to 0.002. And
Okay.
pre-1 con dot delay is equal to 1.
Okay.
But this is giving an error.
Okay. Yes. So there's two little things missing, and the first one is the one we mentioned before that didn't make much sense, but we have to include it still.
The
So it's in
section?
the first line. Yes.
Oh,
So for
okay.
So Robert explained that we still need to include this, which is the section equals basically the same section we have in the first argument, which is
P1 cell
pre-cell.
dot Soma 0.5.
Perfect. Exactly. And then the other error you might be getting is due to something that I didn't explain.
Weight requires subscript. So weight of
yes.
0.
Exactly. So this is also something that comes from the old usage of netcons, where you had several parameters that you could pass. But now, as far as I know, only the index 0 of this array is used. So in any case,
no.
No. Okay.
So this is the state of the synapse, and so the state of the synapse can be arbitrarily complicated. It just so happens in the case of the exponentially decaying synapse, the only state is how strong it is. But like it comes up, it matters in LTP models, any sort of learning models. The vector is automatically populated, except so. Okay.
Okay. Perfect. Thanks, Robert. So yeah, so in this case, we're just going to use the index 0 because that's the one that contains the connection strength. But as Robert mentioned, other more complex models will include other values for plasticity, for example, in other indices. Okay, and the last part was the delay, which was correct. Any questions about this? Okay, so the next step, I think I'm just going to do because it's relatively simple, and it's actually almost indicated here already. So it says fix the voltage plot axis between -80 and 20 millivolts. So that's just to visualize the voltage with a fixed set of axes. Sometimes this is easier. So I'm just going to do pipe plot. Notice that pipe plot we imported here at the beginning from matplotlib import pipe plot. And this is ylim -80 to 20. We could, of course, also include this inside the cell here, where we're going to plot. So we could include it here. And it probably makes more sense. And then the last step would be run the simulation for 60 milliseconds and plot the pre-cell one and post-cell voltage. So let's give a couple minutes to do this. And while you're finishing that, I'm going to start running all my cells. Okay, so the next person I have on my list is Jaran.
Hi. So we're doing 8 right now. Is that correct? Part 8?
Yes. Yes.
Yeah. So I have pre-cell 1 dot record voltage, and then post-cell dot record voltage. After that, I initialize to negative 65 millivolts. Then I continue H dot continue run for 60 milliseconds. After that, I do pre-cell 1 dot plot voltage and post-cell dot plot voltage.
Okay, and let me. So you said to minus 65?
Yes.
And then you said H continue. So the record voltages we did before, so we don't really need to include. We did them here in the first two steps. I'm going to remove those. And then you said continue run?
Yes.
For 60, right?
Mm-hmm.
And can you repeat the last two? You were too fast for me.
Pre-cell 1 dot plot voltage.
Okay.
And then cell dot plot voltage.
Okay. Stop. Okay. Perfect. So I've already run all the previous cells. So if I run this, I think this should work. Pre-cell 1 voltage. So I think the problem is here from matplotlib import pyplot should be as PLT at the top. So inside the class, notice that we're using this PLT package, which is really the abbreviation for pyplot. But when I imported at the top, it was just pyplot. So if you can all add this as PLT here. Probably can also change this for consistency. Step 7 from pyplot to PLT, which is the convention really. And I think, so if we now rerun that cell and We run the last one. Yay.
I also placed the Y limb. I put that in the class because I don't think it updates otherwise.
Yeah, that makes sense. So this line here should really go here inside the class where it says plot voltage. We can add the change of the axis inside this plot voltage function because it makes more sense here from -80 to 20. And you should get this. Just rerun this cell and rerun this last one.
I believe the Y limit must be after figure. The declaration.
Yes, you're right. Yes. It has to be set after you create the figure. And probably after you actually plot the stuff, right?
And actually, you have to run again the presynaptic cell and postsynaptic cell just to adapt the.
Oh, right, because you are creating that. Okay, yeah. So I'm just gonna rerun everything again after making the changes. So I just put the Y limb at the end here of the function before the show, and I'm gonna rerun everything.
And actually, you can create some variables for the Y max and Y min and the definition of plot voltage.
Yes. Yeah, these methods are very simple. So in theory, you should really add a lot of arguments. So for example, to set all the properties of the cell and so on. But this was just like a very simple example. So that it's all like hard coded here, which is not the best approach.
It works. It works. That's.
Okay, so now we have the figures that we wanted. Everybody has these figures?
Yes.
Did anyone have a different thing? If you did, please post a comment on Slack so somebody can help you. They don't look exactly the same, but I think that might be because we initialized the voltage differently. Oh, I don't know why, but pretty similar to the ones I had before. So let me see who's the next in line. Catherine Doxy. So can you maybe try to give a brief explanation of what we're seeing here in this first figure and the second?
Yes. So the top one is the membrane potential at so the blue line is the soma of the presynaptic cell. And then the red line is the action potential in the dendrite of the postsynaptic cell. And then so that's the response after the action potential has gone through or been propagated through the synapse.
Okay, and can you explain what is this little bump here, the red line in the top? I don't know if you see my arrow, but there's like this little bump before the action potential, the red line.
Mm-hmm. I'm not sure.
I assume that's back propagation from the Soma going into the dendrite. Is that correct?
So the dendrite has kind of two bumps. The first one around 20 milliseconds, and then the second one around 25. So it's two different things. Do you know what the first one could be?
Yeah, but it is a presynaptic, right? It's not a postsynaptic.
Yeah, at the presynaptic.
So it's
the presynaptic cell.
It's a stimulation and back propagation.
Exactly. So the first bump is the current injection that we're providing, which is at 20 milliseconds, which is really what triggers the whole phenomenon we're seeing. And then you were correct that the second little bump here is the back propagated action potential from the Soma, which back propagates to the dendrite. Okay, so you see the action potential in the Soma, that triggers the excitatory postsynaptic potential in the postsynaptic cell, which is this that you're seeing here. And it also triggers the back-propagated action potential. Any questions? Okay, so this exercise has a couple of small other parts. So here at the end, it says play with the XSyn and the netcon parameters to get a small EPSP, which we already have done. What we're seeing here is an excitatory postsynaptic potential. B, an EPSP that leads to an action potential. So we want to see an action potential on the postsynaptic cell. And C, an IPSP, an inhibitory postsynaptic potential. So I'll give you a couple minutes to play around with the parameters, and then we can test them here. Okay, so let me see who's next. Heitor Sanchez. So maybe you can give me some changes in values for an action potential in the postsynaptic cell.
To get an action potential, you can change the netcon weight.
Okay.
I changed it to, I removed the 0 to 10 times that 0.
Okay. So I can rerun this and rerun this. Okay, fantastic. So here we have. So we see it's quite a strong EPSP here, arriving at the dendrite and resulting in an action potential in the postsynaptic side. Great. And Claire Short, maybe you can give us some values to get an IPSP.
Actually wasn't able to get that finished yet.
Okay, no worries. So I'll go to the next. Ramohan, you're there?
Yeah, I'm there. I'm still working on it.
Okay, let me just give a couple minutes then.
would you still play with the netcon parameters?
No. So what we want to do is essentially convert the synapse from an excitatory synapse to an inhibitory synapse.
So that will be, we will be changing EX SNYP to IN.
So changing what? Sorry.
Will be changing H dot EXP SYN.
Yes. So you have to change this the post-syn one object. You have to change some parameter of this object, of this synapse.
Salvador,
right
can
now,
I make a question?
Yes, please.
In this graph that we plotted, and when we changed the weight, removing a zero, we don't have action potential in that already. When the second one, when we just removed a zero from, there.
Yeah. Yes, so we get an action potential in the postsynaptic cell, right?
Yes. There is not what we expected to do in the second letter, the letter B.
Yes, that is what we did for B. So now we moved on to C, which is getting an IPSP, an inhibitory postsynaptic potential. Yes.
Okay, perfect.
Okay, so any suggestions for how to get an IPSP?
Reversal potential.
Okay, the reversal potential I'm hearing. Carol.
Should be negative.
Okay, should be negative. For example, minus 80.
80 or 90.
Or minus 90, yeah, whatever. It changes depending on the type of synapse. So if we run this, and run this again, and so we see there's nothing really there obvious, because you might need to have a stronger weight or a stronger negative, more negative reversal potential. But really, if you had ongoing activity where the membrane voltage wasn't minus 65, but you had some other spikes coming or whatever, this would still have the effect of having an inhibitory synapse. So we can just, to make it more obvious, we can increase maybe the weight. So that the driving force overall is a bit stronger. And now you can see it more clearly. Okay, so yes, go ahead.
I tried making the weight negative. Is that, and I did get a negative, but is that like a viable solution, or is it just a hack?
It depends on the model you're building, but we try to keep it biological. So we try to go with changing the reversal potential. But in some simpler models where the synapses are simplified, we have used that negative value in the past. So it depends on the type of model you're building and the level of biological detail you want to include. Okay, so great. So let's move on to the next tutorial, which would be connections tutorial part 2. Okay, so what we're gonna do here is add a third cell, which is gonna be called the presynaptic cell 2, and that cell is also gonna project to the same postsynaptic cell. And essentially, so what we're gonna do is add a new synapse in the postsynaptic cell, add a new connection, a new netcon, and then play around with having two presynaptic cells. So here now we can have things like spatial summation and another couple of things that we're going to try at the end. So let's, sorry, spatial summation and spatial cancellation. We're going to simulate. So the first step, we're going to keep the code from before to create the presynaptic cell 1. Oh, this is not empty. Okay. Oh, well. So you have the first solution to the first part, which is adding a presynaptic cell 2. So the solution is already here, so I'm just gonna go over it. So we are doing exactly the same as for the presynaptic cell 1. We create the HH cell object. We add current stimulation because we still wanna have a spike coming through this second cell. And we set up the recording, all using this pre-cell 2. Okay. Then we have the same code that we had before to create the postsynaptic cell. And now, okay, so I think, we're gonna have to copy some code from before that is missing.
I guess you missed imports.
Yeah, no, I run by mistake, but I just realized we also need to copy some code from the previous one. So
yeah, I mean there are no imports here.
Oh, no imports at the top. Okay.
Yeah, I had the same crash from Neuron import H.
Okay, so let me just maybe make these slight modifications here and upload it again. So this would be I'll just copy these imports over. And I noticed also we're also missing the connections that we had before. So this post scene 1, I'm just gonna put it here. And also the recon 1. So I'm just copying over some of the code that we already had, which creates the connection from pre-cell 1 to post-cell. And if I save this now, yes, I think it should work now. Okay, so I think you can go ahead and make a copy of this collab that I just modified, so you have the same version. So go back to the Google Drive, to the link, and make a copy of this modified version.
So you want post-syn 1 to have a negative reversal potential, or should it go back to 0 like we had initially?
Let me see what was the objective here. We can go back to 0, so make it excitatory.
And do you want the weight back to what it was before with 0.002, or do you want it to be 0.02?
We can go back. We're just going to be playing with these values, but we can go back to the originals. Yes.
Okay.
So just save with those two changes. Thank you.
Yep.
Okay, so you should all have a copy of this same thing I'm looking at here. So I updated and saved on the Google Drive, so we can continue from here. So we have created the presynaptic cell 1, we have created the presynaptic cell 2, and we have created the postsynaptic cell and added the connection between the presynaptic cell 1 and the postsynaptic cell. So we have the 3 cells and this connection here on the left-hand side. Okay, so what the next step that we're going to do is add the other missing connection, which is a connection from pre-cell 2 to post-cell. And that is the step that it's asking for here. So we're going to do these two together. So I'll give you a few minutes to add these two lines, step 2 and 3, which are obviously very similar to what we had before.
I think that we will have the same error that we have to plot the things because in this notebook we used pyplot and imported as PLT, but in the class we use
Okay.
pyplot.
Okay. So what we can do is change this pyplot to PLT. Let me do this here. Yes. So if you select one of them and then press Command D, you select all of them and rename to PLT. So make sure you do that so you don't have errors. Again, inside the plot voltage method, change pyplot to PLT. Sorry about these small issues.
Sorry, Salva, how did you change all together?
So you select one of them,
okay,
and then press on a Mac Command D. So, and each time you press, you create like a new cursor.
And if you're in Windows?
Good luck.
Okay.
It's
I
the
don't know,
same.
sorry. Okay.
Yeah, just blame it on Bill Gates.
Yeah.
Okay, so remember we're doing steps 2 and 3. Okay, so maybe Sonia Ruggieri, you can give it a shot. Okay, great.
Yeah. Yeah, we can define a new X scene. And this will be localized in process cell dot band parenthesis 0.5.
Okay, so you wanna detect the line?
Yeah. So I just wrote like in scene, like inhibitory synapses.
Okay, so I'm gonna call it post scene 2 to be consistent with the other one. Okay.
Equal to H dot X scene.
Okay.
Parenthesis post cell dot then parenthesis 0.5 and then close. And then in the new line, we should define the reversal potential. So as you called, so post scene, so dot E equal to minus 80.
Okay.
And then is post scene 2 dot tau equal to 2 milliseconds.
Okay, great. And thank you so much. And Maria Popova, could you?
Yeah. So pre to con is equal to h dot netcon parenthesis pre cell 2 dot soma parenthesis 0.5 dot underscore ref underscore v comma postsyn 2 comma sec equal pre cell 2 dot soma. And the next line is pre to con dot weight of 0, like in square brackets, is equal to 0.002, and pre to con dot delay is equal to 1.
Okay, fantastic. So we have created the synapse, the second synapse on the postsynaptic cell here, and the connection, the network. So now the exercise asks you to first show spatial cancellation, an EPSP plus an IPSP, and then spatial summation leading to a spike. So for B, what we want to have is that only when you have EPSPs from both presynaptic cells, you get a spike. So we want to show that a single EPSP does not result in a spike. So it needs both of them. Oh wait, we're missing the whole section on plotting. Okay, so let me add this step here. So this would be step 4. Sorry. Run for 60 milliseconds and plot the 3 cells. You can change this to 5. New code line. So this one I'm just, because it's the same as before, I'm just gonna add it here. Okay, so we have to initialize, run for 60 milliseconds, and plot both presynaptic cells. Oopsie. Yes, rerun. Okay. So I've just saved this. So if you're having issues and something's not working, you can just go again to the Google Drive and copy what is there in my Google Colab.
These graphs are the first two are pre-cells, right? The presynaptic.
Yes.
And
The first two are the presynaptic cell 1, presynaptic cell 2, and postsynaptic cell. So we could add some titles to make it easier. Could have like a title thing here, argument. You don't need to do this, but
When you're done with that, do you mind just hovering over the plotting section for 5 seconds so I can get it down? Sorry, I
sure.
came a lot.
No
Thank
worries.
you. Thanks.
So Jessica, which section did you want to have a look at? This one here?
That's all you're doing for the plotting? It's all, okay, I see. Yeah. Pre-cell 1, pre-cell 2.
So don't add this part here. I just added this for.
I just wanted to get the beginning part. Okay, thank you.
No worries. Okay, so hopefully we all are on the same page. So
I'm
let me
getting a
see.
negative. I'm getting an IPSP instead of an EPSP at the post cell.
Okay. Oh, that's probably because you didn't change here these values back to the original. So we had
I did.
this posting.
This
Okay.
is,
0
it's at
and 0.02.
Yeah.
Well, actually, this is what we're going to be playing with, so you can also play with the values. So in theory, with the values I have here, we have an excitatory synapse and an inhibitory one. So mine is 80 and 0. And they both have the same weight. So what we are seeing with those values is that we get an EPSP, right? So how can we change this to get spatial cancellation? So we should see nothing here. The next one I have is Nikos.
Yes, hello. I'm searching for it right now. I think that we should reduce the pre-1 cone weight and pre-2 cone weight. No?
We should reduce which one, sorry?
The weights for the pre-1 cone and pre-2 cone.
Okay, both of them.
Yeah.
Okay, give me values and let's try it out.
Let's reduce them 10 times, let's say.
Okay, so what is the rationale for making this change to get a spatial cancellation? Why do you think that is needed?
Because if we do that, maybe the signals are too weak to create an action potential or anything in the postsynaptic cell.
Okay, so that's true. So if we reduce both by 10, we're probably not going to have anything, but not because they are canceling each other, but just because we don't have anything. So what we're going to do is have an EPSP and an IPSP that cancels the other one.
Yeah, I see. We need a cancellation. Okay, now I get it. Could you please give me a couple of minutes to...
Yeah, sure, no worries.
You see that? Yeah, thank you. You actually can reduce the weight of... sorry, increment the weight of the inhibitory. It's just like that.
Okay. Perfect.
Just a little bit. I mean 0.008, and that's enough.
Okay, so let's try that. So we increase the weight of the inhibitory synapse because we are seeing that even though we have both of them, the positive excitatory synapse was still sort of winning, and now with the inhibitory synapse stronger, we actually see sort of more clear spatial cancellation. Okay, great. And now part B, we want to see spatial summation leading to a spike. And again, this we have to show that the spike only happens if you have input from both synapses. So you shouldn't have like a really strong synapse that generates a spike by itself, but requiring both, summation of both to lead to a spike. So of course, for that, you're gonna need both synapses to be excitatory.
Yeah, just to add, if one of the presynaptic, I mean, if one of the postsynaptic, if one of the synapses has a reversal potential that is equally distant from the F initialize, I mean, if it's minus 130, that is 65, it will be a flat line, completely flat line, because the two synapses will have equal driving force, but each one for not equal, but they will cancellate perfectly.
Yes, exactly. The driving force of the excitatory synapse is stronger because it's further away from the resting membrane potential, so it's 0 millivolts versus -65, so it's a strong driving force. Whereas the inhibitory synapse, we had it at -80 or something, so it's pretty close to the resting membrane potential, and so the driving force is smaller. Therefore, you need a stronger weight to make them sort of cancel each other. Okay. So anyone for the spatial summation, you want to give this one a try, Nikos?
Well, the thing I did, and I actually took an action potential, is like I increase in time the weight of the excitatory synapse, but I'm not pretty sure that this is the one we are looking for.
Okay, so let me see. So first thing, we need to make the second synapse excitatory. So we set this post-syn 2E to 0, so that both synapses are excitatory.
Oh, so we have to do that?
Yeah, because the exercise is to have two excitatory synapses that combine, summate, the EPSPs summate to produce an action potential. Okay, so we want to have two EPSPs initially. That combine result in this spike. And let me just put the values to the original value, which was 0.2. And let me just try to run as it is. So with the original value. What's going on here? Okay. Okay, so if we just change both to EPSPs, to excitatory synapse, it actually works. But let's check if it's matching the condition that we wanted, which is that it doesn't work just with a single synapse. So we can just, for example, set the strength, the weight of the second one to 0, just to check. And we can rerun everything again. Okay, so yeah, this actually, we didn't really have to play much with the parameters. So I set one of the second synapse to 0, and you got an EPSP. And when we set it back to the value 0.02, you get two EPSPs that summated result in a spike. Okay. Of course, it is possible that if you had lower values, maybe 0.01 in both, you might still get an EPSP that doesn't result in a spike. Okay, like in this case, you now have two synaptic inputs which don't result in a spike, or you could have a single one. So if we set the second one to 0 and we have a very strong one here, 0.02, then you can have a single synaptic input that also results in a spike, which is again not what we were looking for. Okay, any questions here? Okay, so let's move on to the last part, tutorial part 3, connection tutorial part 3. Let's see. Let me just double check here. Okay, so here we're missing the last part as well. So I'm just going to update that, make sure everything works. Okay. PLT, and this part here. Okay, so I think that should be okay. So make sure I'm gonna save and make sure you make a copy of this last version that I just updated. Oops, wait. Okay, now you can make a copy. Because we're starting from the same step we were in the previous tutorial. We have these two cells, presynaptic cells connected to the postsynaptic cell. And what we're gonna do here, I'll give you a few seconds to make the copy. Okay, so what we're gonna do here is create a recurrent network. So the two inputs to the presynaptic cell are gonna generate spikes in the postsynaptic cell, and then we're gonna connect this postsynaptic cell back to the initial presynaptic cells. So creating a loop on both sides, and so creating essentially infinite spikes on all three cells. Okay, so let's look at the code. So the first cell here is just some of the code from the previous exercises to create these three cells. And the first step here says adjust the parameters to make both synapses excitatory. And so the postsynaptic cell fires due to spatial summation. So this is actually what we just did as well. So I'm just gonna change, so make sure this is 0 millivolts, so that we have both of them are excitatory synapses. Okay. And we move on to step 2, which is adding the new synapses. So these synapses, notice they're gonna be on the presynaptic cells. So we wanna synapse on the presynaptic cell 1 and on presynaptic cell 2, so that we can create these recurrent connections. Okay. From post cell back to pre-cell 1 and from post cell back to pre-cell 2. So let's try to do that. Step 2, add an excitatory synapse to each of the presynaptic cells at location 0.5 of the dendrite with a tau of 2 milliseconds.
Is POSIN2 an excitatory synapse or an inhibitory synapse?
Excitatory. So we want both of them to be excitatory, just like at the end of the previous tutorial.
Can I just ask about the nomenclature for 2? Would you want to call it Presyn 1 and Presyn 2, or did I miss something important from before?
So we want to call it pre-1 syn because it's the presynaptic pre-cell 1 synapse.
Okay.
So, and the pre-cell 2 synapse.
Okay.
The 1 refers to the cell, not to the synapse. That's why the 1 is before.
Okay.
So what is the use of the function exp2 syn?
What are the what? Sorry.
So we use the function like h.exp syn, right?
Mm-hmm.
So there is one more which comes up exp2 syn.
Oh, that's a double exponential synapse. So it has some time constant at the beginning, a rise time, and a fall time. Okay. And the X syn only has a fall time, I believe.
Got it.
Okay, so next in the list here I have Laura Medlock. Want to give it a shot?
Yeah, for sure. Just doing the first one or both of them?
You can do both.
Okay. So pre1 syn, yeah, equals h dot x syn brackets pre-cell 1 dot dend 0.5. And then the next line will be pre1 syn dot e or tau. Yeah, sure, that's fine. I assumed we wanted to define that it was excitatory, so 0. Yes. And then pre1 syn dot tau is 2. Fantastic. And then the second one would be identical, but you just swap out the 1s for the 2s.
Yes, gonna copy. We don't want to write more than we need. 3, 2, 3, 2, 3, 2.
And then just the pre-cell, yeah.
Okay, great. Thank you so much. So this is creating these 2 synapses here, this guy and this guy in the presynaptic cell. And now to create the connections. Okay, so here are the connections that we had before. We don't need to modify this. And now we want to create these 2 new connections. So that's step 3. Connections going from the postsynaptic cell to the presynaptic cells. And I have next in the list Monica BB.
Yeah, hi. So for creating the post connections for postcon 1, it's h.netcon open bracket postcell.soma 0.5 dot underscore ref underscore v comma pre 1 sign comma sec equals postcell.soma close bracket. Sorry, was that too fast?
Trying to give up. Sec equal postcell.soma, right?
Yeah, and then
okay.
Postcon 1 weight 0, I still use the 0.002, and then for the postcon 1 dot delay, I put 10.
Okay, cool. Perfect.
And then for the second one, I repeated the exact same thing, but just changed all of the con 1s to con 2s.
Perfect. So we can do this. Okay, great. So I think we got it. Any questions? So now let's try to run and see what we get.
Need a capital C in NetCon?
Yes, thank you. Okay. Ooh. Okay. So what are we seeing here? Let me see. Who's next? Amanda Araujo.
Hi.
Hi there. So you wanna try to explain what we're seeing here?
I can try, at least.
Yeah, sure. So we have the two presynaptic cells here, presynaptic cell 1, presynaptic cell 2, and the postsynaptic cell. So let's start maybe with these first sort of spikes that happen at around 25 milliseconds. Do you know why those are caused?
For the first cell, we see a actual potential because it received a stimulus like before.
Okay.
So we have for the cell for the pre-cell 2, and these stimulus from these cells are able to provoke actual potential in the post cell. But due to the loops we created, we see that in pre-cells 1 and 2 we have a second type kind of response due to the link with the post cell.
Okay, fantastic. That's exactly right. So this second response, it's an EPSP, right? It happens around 35 milliseconds more or less. But it doesn't reach a spike, so it doesn't reach the threshold to generate an action potential. So do you know what we could change to make these generate spikes?
Maybe we could change the weight of the new links we created. Maybe the weight of the post connection.
Okay.
I don't know, to 0.02 maybe. I don't know.
Okay, so 0.2. I'm gonna change one or both.
Both? I don't know. Let's see what's happening.
Okay, sounds good. Let's try that. So I increase both of these connections, which are these guys here. I increase the weight. So let's see if we now run everything. So to run, by the way, I'm using this keyboard combination, Command-Shift-R, which I had to change in the settings here somewhere, because the default was Command F9, and I have no idea where F9 is in my keyboard. But you can also go just to runtime and run all. It's the same thing. Okay, so let's see. And fantastic. Now we have exactly what we wanted. So by increasing the strength, now we're, well, you want to try and explain what we're seeing now, Amanda, just to finish off?
Now I think we the first two pre-cells were able to provoke an actual potential in the post cell. Then these post cell are able to induce an actual potential in the first two, the pre-cell 1 and the pre-cell 2. And then they just propagate this, like they return signal to the post cell that returns back to the pre, and then we have an infinite loop, maybe.
Yes, perfect. We have a recurrent infinite network, which of course is not very biological, but in theory we would be able to get one. So something interesting to do is to increase the duration to 200 milliseconds to see that it goes on for a bit. So if you run that, it takes a bit longer, of course. It's running. No, sorry. Yes. So yeah, so if you run for 200 milliseconds, then you see all these spikes happening in the first and second cell, and resulting in this recurrent network. Any questions?
This is the principle to build a CPG network and neuron.
Exactly, yes. This would be similar to a central pattern generation, which are used for locomotion and these kind of things. This, of course, is a very simple, idealized example, but yes.
Perfect, thanks.
Okay, so if we don't have any more questions, we can finish here today. That's perfect, 7:03. And the next 3 days, we will see how to build this kind of networks using NetPyNE. So tomorrow we're going to see the GUI, the graphical interface, which is the most easy way to start. And then Thursday and Friday, we'll see more of the programmatic scripting NetPyNE interface and some more advanced features. Yes, Suri?
If we make any one of the weights 0, there will still be an action potential. It won't spike, but there will still be action potential. Is that because the other weights are kind of stepping?
Yes. So in theory, the exercise was that if you set one of these to 0, it shouldn't result in the recurrent spiking.
But there will still be spiking, right? There will still be one spike at least.
Yes, so you will get the first one in the 2 presynaptic cells, because that is generated by the current, and the first one in the postsynaptic cell, because that results from this. Oh, that results from, in this case, oh, sorry, I set only the postsynaptic, the connections that go back. So in this case, you only get the spike on the presynaptic cell 1 because I set the other one to 0. So this one is not getting connection back. But I think what you were referring to is if we change this to 0.
I changed pre-1 con to 0.
Okay, yeah, same thing. And then you should get this, right? So you only get the 2 first presynaptic spikes and no postsynaptic cell.
Yes, yes. That's
Okay. Well, thank you so much, everyone, and I'll see you all tomorrow.
Thank you a lot.
Thank you.
Thank you.
Thank you.
Thank you.
Bye bye.
Very clear.
Thanks so much.
Thank you. Bye bye.